Namaskar, my dear friends. So we have been seeing in switching regulator training sessions, okay, and we have seen a lot of DC-DC converters, very high efficiency DC converters, many kinds of like switching regulator as a buck converter or boost converter or whatever we have, right? So what we'll do is we'll try to take up three applications, okay, for the solutions of maybe like automotive battery regulations or power for portable products or industrial supplies or industrial sensors. So many like automotive supplies as well. So we'll try to like take up like this. We have three ICs which is like LT3970. Those applications are as I already mentioned just now, and we have LT8604 which will be industrial sensors, industrial internet of things, or 4 milliamperes to 20 milliamperes current loop designs, flow meter design, automotive housekeeping supplies, basically like low end applications, okay, small appliances. And we have very high current applications as well, using this ADPL 13602, which will be industrial control supplies or distributed power supplies, wall transformer regulations, or high voltage single board systems, right? So what we will do is, with these three applications we have already given you a lot of design implementation, right? Design implementation. So in this session what we will do is we'll take up one of the IC which is LT3970, and we'll try to design how we can like complete what is the input voltage, output voltage, and we can design the complete circuit, right? So let's get into this particular part number, which is going to be LT3970. So as you can see, this can take up to 40 volt input, so this is quite wide range, and it is going to give us 350 milliamperes of step down regulator with 2.5 microampere quiescent current, which is very good, and it has integrated diode, so you don't have to give you like or integrate, I mean, design for external diode as well, like there is no need of catch diode or something like that. So in the simple switching regulator design, what is the thing that we have already learned is we need to understand what is my input voltage, what is my output voltage required, and I output current requirement, right? So based on this we need to choose what is my capacitor, what is my output capacitor, like input capacitor, output capacitor, and what is the feedback voltage that will be there, which will be mentioned. Let's say it is 1.21 volt or 0.8 volt. Generally it is there in the data sheet of the uh, IC, right? So based on that we will be deciding what is my voltage divider resistor, and that actually in turn sets the voltage output, okay? And one more thing, the last we will be doing is inductor selection. Inductor selection. So if you want to make your design very quick and very accurate and no mistakes should be there, sturdy design, the only thing that you have to understand from the switching regulator data sheet is these are the 5-6 parameters which should be mentioned, right? So once you are taking care of these 5-6 parameters, then your design will be very sturdy and it won't go wrong at all, okay? So let me give you just quickly one typical application circuit that is given in the data sheet itself. General rule of thumb you keep is, let's say we have the input voltage, it can be like 12 volt or maybe sometimes 15 volt or 18 volt or 24 volt, you know, even it can take a 30 volt as well. Up to 40 volt it has the rating, but up to 30 volt is fine, okay, for practical applications, right? So this is the input voltage that we have done. General rule of thumb, what you do is you always try to keep input capacitor. If you are using electrolytic, then you can keep it like 100 microfarad or even 220 microfarad, okay? If it is ceramic, then you can keep like 47 microfarad or like 22 microfarad, okay? So this is the rule of thumb that you can keep, okay, first. And plus zero point 0.1 microfarad capacitor always you give. It will actually help you to design the input capacitor with low ESR values, because ceramic capacitors has low ESR. So even if you are using electrolytic capacitor, it will maintain that ESR values, okay? Coming back to output side, so output side also based on the current requirement you can increase the capacitor. So add plus 0.1 microfarad capacitor In addition to that, with if you want, you can increase this particular values to one more parallel capacitor. Okay, so one more parallel capacitor you can keep, which is, let's say, 22 microfarad. So this is how you are going to design your input capacitor C in and your output capacitor C out. The only requirement that you have to understand about input and output capacitors are voltage ratings. Okay, so let us say you have a 12 volt system, then minimum your voltage rating should be twice of that, around 25 volt, or like a 35 volt ratings. Okay, if you have a 30 volt system, then also you can go ahead with let's say 50 volt rating, or maybe 63 volt ratings. So that is more than enough. Okay, at output side, coming back to output side, it is 5 volt rating, so you can go ahead with a 10 volt rating of capacitor, or maybe 16 volt rating of capacitor, even 25 volt rating of capacitor, but do not go less than 10 volt. The thing is, if you are using electrolytic capacitor, then definitely you have to go ahead with 25 volt or more, because at 10 volt or 16 volt it will be like its value will be very less. Okay, basically the derating curve is very bad for ESR, I mean electrolytic capacitors. Okay, so you have to go ahead with higher voltage ratings. Next is we have to have enable functions. Enable function, you can directly connect it to input voltage, so that you don't have to worry about enable disable the IC. If you need this particular functionality, then you can keep it connected through one resistor. Okay, and then connect it to input voltage, or maybe if you have other voltage, then you can keep it 3v3 separately and then send it to your microcontroller MCU. Okay, this is a power good application. No, not this one. This is, one second. What you do is, here this was enable pin, so enable pin you can just keep it connected to the input voltage. There is no need at all. Or otherwise, if you want to connect it through microcontroller IOs, then microcontroller IOs will be coming up here and switching it on, so you don't have to connect this particular input here. Okay, so microcontroller will take care of that. Coming back to this power good, so power good is basically going to introduce or give you an understanding that my output is within the range or not. Okay, so for that you can pull it up with some 3v3 and then send it to microcontroller IOs. So whenever it is high, it will tell you that okay, the power output is correct. Whenever it is low, then there will be fault condition identified. The very important thing is, what is the frequency that you want to work at. So based on resistor setting values, you will be getting a table of frequency settings, or you have a formula to set the frequency of operation. Okay, so these resistor settings will be always given in the datasheet. That also we'll see quickly. We have a boost capacitor. So boost capacitor is connected to the switching pin, which is going to be increasing the voltage input for driving the MOSFET internally. Okay, so this is how it is connected. If it is output is less than 2.2 volt, then boost pin is not boost pin must be connected to SW pin, and there is a requirement of selecting the inductor. That also we have the formula for that. Coming back to BD pin, so BD pin, there is a capacitor required connected to be with the FB, or otherwise if it is output is less than 2.2 volt, then BD will be connected to V in. Okay, that will show you. Last thing is, we have to set the output voltage. So output voltage setting will be done in the adjustable regulators. That will be done through, let us say this is my R1 and this is my R2. So R1 and R2 value will be calculated based on the FP value that you already know, which is 1.21 volt for this particular IC that I will show you. So this is complete design that you have understood within 2 minutes. Okay, got it. Now let us get into the data sheet of this particular device and try to understand and catch some of the parameters that we need. Okay. So I have opened for you this particular device data, product series or product page, which is LT3970. If you can open analogdevices.com, okay, analog.com, and just go to search and put down your part number LT3970, and it will give you this particular page. Okay, So as you can see, it is having 40 volt 350 milliamperes step down regulator with 2.5 microampere quiescent current and integrated diode. Most of the informations are already given in the product page itself, so you don't have to worry about and go somewhere inside the data sheet. So you can see one of the application will be given, then efficiency will be given, different part numbers, pin configurations are there, which is DDP pack, like DFN package it is, and it is like MSOP package. So there are two packages that is there with this particular device. Okay. We have features listed here, so it is very easy to understand from the product page itself whether we should go ahead with this particular IC or not. Okay, it is AAC Q100 qualified for automotive application also. This particular IC can be used for your automotive application as well. Now coming back to some additional information, so you can see whether it is a adjustable regulator or fixed regulator, and what are the different packages available, and what is the main important thing in this product page is what is the application that is given directly, like this can be used for this particular application circuits. Okay, you have the pricing and everything. So this is how the same thing is given in all other manufacturers as well. Let us say it is either in Texas Instruments or NSAS or like Microchip, any manufacturer you take, all the switching regulator or any other data sheets, all the informations are given properly. Now let us get into the design. So I will open the data sheet for this particular device and we'll get into the understanding of what are the information that we need to design our regulator. So you can put here view data sheet, so it will open data sheet for you. Okay. Now I have opened this data sheet, so as you can see very boldly it is written that what is the description of this particular IC, so that we have already seen. Now let's get into the features. So features is very low ripple burst mode operation, so it is in burst mode operation with very low IQ, that is quiescent current, which is 2.5 microampere at 12 volt input to 3.3 volt output. Okay. Now output ripple is just a 5 millivolt peak to peak, so this is quite good. Okay. Coming back to the input side, so we have input operations from 4.2 volt to 40 volt, so you can have like up to 40 volt input at the input side. Switching frequency can be set to 200 kilohertz to 2.2 megahertz. So generally I prefer to go ahead with let's say 600 kilohertz or 700 kilohertz, that is more than enough for our design, or maybe 1 megahertz max or 1.2 megahertz. Okay, don't go ahead with more than this, otherwise efficiency actually decreases. However, you can have an understanding of by increasing the frequency of operation your inductor size will be reduced, but my suggestion always is keep the frequency little bit nominal, so that your design is sturdy and you don't get into the unstable designs. Okay. It has integrated boost and catch diode, so there is no requirement of diode selection for your catch operation. We have 350 milliamperes of output current, so this is quite good IC for low output or low current applications. Okay. The best thing is it has a fixed output voltage variations also, which is 3.3 volt and 3.42 volt and 5 volt. Okay, so these are the three fixed operations, and we have adjustable operations up to how much output voltage can be set from 1.21 volt to 25 volt. Okay, we have enable pin which can take 1 volt to make it enabled. Coming back to the power good flag, so as I told you, like output is within the range, let's say plus minus 5% or something, which is mentioned in the data sheet, then we can see that power good is good, like the output is within the range and it will give you high, otherwise it will pull it down, that it will make it low, and this is how you will understand that my IC output is not correct. Okay. It has a small 10 pin MSOP package and a DFN package, so two packages are there, and this particular IC, as I already mentioned, that it is qualified for automotive application. Okay, good. If you want, you can go ahead with description, but there is no need. We have already seen a lot of features and understanding of this particular IC, so there is no need to waste time in studying this description. Okay. but description is always important. If you have time, you can like read it and understand that what is the particular understanding about this particular data sheet. I already explained you what is the typical application. So typical application you already know, like what is my input voltage and what is my output voltage setting based on the adjustable regulator. So these two resistors has to be designed, this inductor has to be designed, the output capacitor has to be designed, input capacitor has to be designed, and frequency of operation has to be designed. This much, like number 1, number 2, number 3, number 4, and number 5. So these 5 parameters to be designed, more than enough, and you can keep these two values fixed almost for all other voltage outputs, so that is more than enough. So these 5 parameters are enough to design your complete switching regulators. And as you can see, we have a efficiency which is reaching up to more than 85% or something at higher current, okay, more than 100 milliamperes of current. For low current, if you see here, for lower current we have let us see, this is left side is efficiency, right side is power loss, okay. So efficiency is reaching at 0 0.1 ampere current, or point 0.1 milliamperes of current, or 0.2 milliamperes of current only, it is reaching more than 70%, okay. If you are consuming more than 100 milliamperes, then it is reaching more than 80% of efficiency. So the red one is for efficiency, the blue one is for power loss. So maximum power loss that you are seeing is 100 milliwatt, okay, at 100 milliamperes of consumption or something like that. So this is how this complete understanding is, okay. So this design was actually for 12 volt input and 5 volt output, that you can see from left side, just now I showed you, right. So this is the way we see the efficiency curve. One side is power loss, one side is efficiency. Now let's get into the other parameters of this particular IC. So very first thing that you have to understand is absolute maximum rating. Like what are the pins? Different pins are there, like input pin, enable pin, they can take maximum 40 volt, okay. Boost pin can accommodate up to 55 volt. Boost pin above SW pin must be 30 volt. Like suppose SW pin is 5 volt output, so boost pin must be 35 volt, not more than that. That's the understanding of boost pin above SW pin, okay. Coming back to FB, like feedback out and RT voltage, it will be maximum 6 volt, it should not be more than that. PG pin and BD pin must be 30 volt or less. We have 3 grades of ICs, which is E grade and I grade, that is extended temperature grade and industrial grade. They work up to -40 degree centigrade to 125 degree centigrade, right. We have H grade IC also, which can work up to 150 degree centigrade, and we have lead temperature soldering, so MS only, which will be 300 degree centigrade, it will be taking for the soldering. Now coming back to pin configuration, so pin configuration, if you see, we have DD package, that is DFN package, which is of 10 pin. So we have FB pin, enable pin, input pin, 2 ground pins are there. We have SW pin, which will be connected to the output of your inductor. Then we have boost pin, we have BD pin, we have PG pin, and we have RT pin. PG pin is power good pin, and RT pin is setting the switching frequency. Similar to that, we have MSOP package, almost same pin to pin complied, but the size will be differing, correct. So same pin configuration is there. We will see the pin definitions, and if it is needed, then you can understand. The understanding is FB will be there for LT3970, which is FB is here, this one, and if adjustable is not there, this is adjustable. If adjustable is not there, this is fixed one, okay. So fixed one, the part numbers will be LT3970-3.3 or 3.42 or -5, okay. So this FB pin will be converted to Vout pin for a fixed one, and it will be converted to FB pin for the adjustable one, okay. Similar to that, MSOP package as well. Good. So coming back to the device information, or if you want to order the informations, you can have DFN package. Okay, DFN package. So DFN package is nothing but DDB. You can see DDB. So it has two temperature ranges, one is E grade, one is I grade. Okay, similar to that MSOP package also E grade, I grade is there. So these are all adjustable one. Coming back to the fixed voltage rating, so fixed voltage you have H grade also, like high temperature range. We have 3.3 volt ratings, and we have 3.2 volt, 42 volt, and we have 5 volt. Okay, so these are the devices that is there with you. So if you want, you can have which device you want to utilize for that. So 3.3 volt you can go ahead directly with I, and for 5 volt you can go ahead directly with IMS. Okay, so IMS is nothing but it is MSOP package with temperature range of up to 125 degrees centigrade. It is given here. So these two parts you can take up for 3.3 volt and 5 volt. For adjustable one, you can go ahead with IMS has PBF. So IMS has PBF. Generally these three devices I have utilized in various applications of our automotive applications. Automotive application part number, if you want, you can go ahead with WPBF. So there is only change that in automotive parts are has WPBF. Okay, so this is without W and this is with W, means it is automotive part. So generally automotive parts these also can be utilized if it is not required exactly automotive part. Okay, otherwise if you have to have a complement of automotive parts, then you can utilize same way this one. So what will happen, for 3.3 you can use this part, for 5 volt you can utilize this part, and for adjustable one you can utilize this part. Okay, so as you can see, MSOP part is only applicable for all the automotive grades. These three parts I had used for my applications. Let's go next. We are having electrical characteristics. So electrical characteristics, very important thing is what is the minimum input voltage that is needed. So 4.2 volt must be given, otherwise there will be a problem. You cannot work with this IC less than 4.2 volt. Then we have feedback voltage. So feedback voltage is set to 1.21 volt. So you have to understand that 1.21 volt we have to have at the feedback pin. So based on that only we will be designing our resistor R1, R2, considering this my Vx or VFB is 1.21 volt, and based on that we can decide our V output accordingly. So based on V output we will be designing my R1, R2 and VFB. Okay, VFB. Good. For a constant output voltage like 3.3 volt or 3.42 volt and 5 volt, we have given like what is the typical output that you are getting. So they are just very accurate, 3.26 and 3.34, just 0.04 volt up and down. Okay, but you will get proper 3.3 volt. Similar to that, other tolerances are also given for 3.42 volt and 5 volt. FB pin current is FB pin voltage is 1.21 volt, so current is just 0.1 nano amperes. Switching frequency, they are telling you like if you want to set it 2.25 megahertz or 800 kilohertz or 200 kilohertz, some three values they have given you. Okay, so if you want, you can utilize this particular RT resistors for setting this particular switching frequency, but this is not needed. I will give you the table where you will be having proper understanding. Rest others are almost same. You don't have to worry about much. Now switching on time and off time is quite less, so we don't have to worry this about which is just 90 nanosecond. Now what is the other information that is there with this particular device is typical performance characteristics. Okay, so in typical performance characteristics, basically you will see that what is my load current, like 0.01 milliamperes to up to around how much, 100, 200, 300, so around 350 milliamperes that is given at last, right? And this is the efficiency. So you can see if your input voltage is lower, then it will be higher efficiency, and if it is little bit higher, then it will be lower efficiency. So you can see green color, which is 36 volt input, then your efficiency is little lower, which is going to around at 1 milliamperes of current, it is just above 60%. But for 12 volt, it is quite high. So you can see it is more than 70% efficiency for 3.3 volt. Okay, so make sure, like let's say 12 volt input is there, then 3.3 volt is sufficient. But if you have 18 volt input or 24 volt input, then directly converting to 3.3 volt may lead to lower efficiency. So you can go ahead with, let's say, converting to 5 volt first, and from 5 volt you can convert it to 3.3 volt. Okay, that's the understanding of proper efficient switching regulators. Same way you can see, we have 5 volt efficiency, and we have feedback voltage. Now let us talk about feedback voltage. So based on temperature, the feedback voltage actually varies. So feedback voltage is there in this y axis, and x axis is my temperature. So my temperature variation is minus 50 degrees centigrade to 150 degrees centigrade, and you can see my feedback voltage actually remains within 1.21 volt to 1.20 volt. Okay, so it's very accurate, like there is no much variation at all. Output voltage tolerance we already saw in the electrical characteristics. So you can see it is 3.29 volt, like more than 3.294 volt or something, and it is upper side, it is 3.34 volt that we have seen. So 3.34 volt, and it is 3.294 volt. Okay. So 3.3 volt is quite accurate. Similar to that, we have 3.42 voltage output and 5 volt output. So you can see 5 volt output, it is 5 volt, and 4.97 volt, something like that. Good. So other, like performance characteristics is there. So let us say no load supply, and also this is not needed. We'll tell you which is important. Okay. Let us say load regulation. So load regulation, you can see we have this one, like load regulation percentage. So lower the load regulation percentage, better the IC. Okay, so you can see just 0.15% maximum, and negative side is minus 0.07% or something, minus 0.07% or something. Okay, with load current, whatever the maximum current that I am consuming, which is 350 milliamperes. Okay, so this IC will be generally used for designing your, let's say, 200 milliampere current rating or 100 milliampere current rating applications that is needed. Okay, up to 300 milliamperes is applicable. So 100, 200, 300 milliamperes of current requirement applications, this IC is quite good. Okay, so this is how we are understanding this particular IC. Let us talk about some other applications. So we have, boost pin current rating. We don't have to understand. If you want to go very deeper, then only you have to understand these things, otherwise there is no need. Now minimum input voltage that is needed to have a V output of 3.3 volt, that is shown here. It is just below 4 volt. Okay, it can work. Okay, so just below, so 0.7 volt is needed to the difference. Okay. Same way you can see for 5 volt, you just need like 6 volt in the beginning. Okay, or 5.5 volt to run, and to start you need 6 volt, and you have to have more than 5.5 volt to have a 5 volt input, 5 volt output. Okay. Okay, so various other like characteristics was there. Now coming back to enable threshold. So enable threshold, as you can see, for various temperature ranges, my enable threshold is close to 1 volt. So if you give more than 1 volt at the input, your IC will be enabled or IC will be started. Now coming back to switching waveform. So load transient response, what happens is, let us say we have a V output. Okay. So V output, as my current increases, let's say at the beginning it is lower current. Okay. Now as soon as it increased, like my current increased here, as you can see, there is a slight glitch in the output. So you can see 100 millivolt per divisions. In one division it is 100 millivolt. So close to 50 millivolt drop will be there. And as soon as my current requirement decreased, then again it gave one like a transient, or like a little bit overshoot, and this is how it got. So as soon as my load current reduced, the voltage increased slightly by like around 50 millivolt, and it gave you the, after that it gave you the exact operation, exact output. Okay, so this is for 5 volt. Similar to that for 3.3 volt and other voltage also it will be there. Okay, so this is how the performance characteristics were there. Now let's get into the designs. So first of all you have to understand pin definition. So as I already mentioned, this is my feedback pin. So feedback pin, how like we have to connect resistor divider to tap this pin output. Okay, so FB pin is 1.21 volt, you have to remember. We have V output pin. So V output pin, you know already that we have some fixed output voltage ratings, and otherwise we have adjustable also. So dash X will be having like a V output, and FB will be having without dash X. Okay. We have enable pin, we have input pin, we have ground pin, we have SW pin, which where you have to connect your like inductor to the output. We have boost pin. So boost pin is just basically used to drive the voltage higher than input voltage. Okay, so what does it mean is, what does it boost pin means is, let us say your V input is like 12 volt, but you need little bit higher voltage compared to that pin to drive the MOSFETs internally. So at that time boost pin actually helps. Okay, so that's the reason boost pin to SW pin there is a capacitor that is connected to boost it. We have BD, that is boost diode. So anode of boost diode is actually connected to the like internal regulator, which is going to give you more than 3.2 volt. We have power good indicator pin, which is actually like open drain. So open drain, if you want to monitor the power good, then you have to have PG pin pulled up with, let's say, 3.3 volt, and send it to, this is my PG pin, send it to your MCU IO. So 20 kilo ohm you can put, and you can send it to the microcontroller input output pin or GPIOs pin. Okay. Now PG is valid when V input is above 4.2 volt and enable is high. Then only PG will be valid. Otherwise, like PG remains low until FB pin is within 10% of the final regulation voltage. So see what is there. It is telling you when PG is low, it means it is good, like the output is good. Okay, and when PG becomes high, then there will be a fault detection, like output is not good, output is not okay. So within 10% of final regulation voltage, PG remains low. Okay, I think I told you in the beginning that PG goes low when there is a fault, but no, PG remains low when there is a good condition, and it goes high when there is like a default, or fault in the output. We have RT pin, which is going to have a resistor to set to the ground to set the switching frequency. So this was all about pin functionalities. Now let's get into the next one, which is my block diagram. Very good. So block diagram, if you have a good understanding about block diagram, you know what is your system, right? So you can see we have input, so input capacitor is needed, and we have output, so we have like SW pin. So there you have to have one inductor and one output capacitor. So output capacitor one they have shown, but generally I have already told you like how many capacitors will be needed and how capacitor values are designed, right? Then coming back to this is enable pin. So enable pin, how it works, you can see we have a comparator here. So as enable goes more than 1, then it goes like a output at shutdown, and it pulls it down, and this pass transistor allows the input voltage to go to the output, right? Coming back to this RT pin, so this is RT pin, which is going to set the oscillator from 200 kilohertz to 2.2 megahertz. You have to put exact resistance so that you can put like set your switching frequency of operation. We have power good output, so which is open drain output. So if you want to take output to the microcontroller, then you have to pull it up through some resistor. So this is the complete operation about this particular block diagram. We have like a BD pin, that is boost diode pin or something like that. We have boost pin, we have SW pin, and then coming back to the output pin here, so you can see For fixed ones we will be having output, and for which where feedback resistors are built in inside. Okay, now for adjustable one we have FB pin, which will be allowing you to design for these two resistors, which is R1 and R2. Okay, so this R1 and R2 you can utilize or you can design to have your particular output voltage at this point. So this is the complete block diagram that you have understood now, how to set this enable pin, and what is the oscillator frequency, or what is the like a boost diode or boost pin to supply the input voltage or supply to the like in internal MOSFET. Okay. Now if we move to operation, so operation we have lot of theories that is not needed much. I'll just directly tell you like what is the thing that is required. So application, you have to set this particular thing in your mind, like how to set your output voltage based on the like output required. Okay, so if you want to calculate your R1 values for, let us say, 5 volt output, then set R2 values to be, let us say, like 130 kilo ohm or 150 kilo ohm. Okay, let's say 150 kilo ohm you put, then you have to have 5 by 1.21 minus 1. So you calculate this particular formula and you will get the value of R1. So R1 and R2 is designed. That's all done. So this is my first step. Next step is setting the switching frequency. So setting switching frequency, what will you do? From 200 kilohertz to 2.2 megahertz you have the options. So if you want, you can directly choose one of the value from this particular table. So let us say I want to set it for 0.8 kilohertz, sorry, 0.8 megahertz, that is 800 kilohertz. Then you can set the values to 158 kilo ohm. Okay, if you want to work with 1.2 megahertz, then 100 kilo ohm you have to put at RT value resistor. Okay, so operating frequency trades-off, you already know that selecting the operating frequency is a trade-off between efficiency, component size, and minimum dropout voltage and maximum input voltage. Okay. So advantage of high frequency is what? Like suppose you want to work with higher frequency, let's say 1.2 megahertz. So what is the advantage? You have a smaller inductor, I told you very beginning itself, and capacitor values also will be smaller. So capacitor requirement and inductor requirement will be smaller, but disadvantage are lower efficiency. So if you want to, if you like high efficiency, you have to work with lower frequency. Otherwise for higher frequency there will be lower efficiency. Okay, the highest stable frequency is SW max for a given application can be calculated by this formula. Okay, so basically V output, how much it is needed, plus VD, that is dropout voltage, and T on minimum multiplied by V input minus VSW plus VD. Okay, so you can see here VD is the integrated catch diode drop, which is 0.7 volt. Okay, so that you don't have to worry about, and generally my duty cycle is V output by V input ratio, and this is the efficiency. Okay, okay, so this is the particular formula that I told you to have the understanding, like how much switching frequency you should set maximum by using this particular formula. Okay, so let us say you want to utilize 5 volts, so 5 volt plus 0.7 divided by T on minimum will see multiplied by 12 volt, let's say, is my input volt, minus VSW is almost 5 only, plus 0.7. So T on, if you are working with like 100 kilohertz frequency or 400 kilohertz frequency, you can work with that. What is the duty cycle that you wanted? So you know already this is my F, then this will be my 1 by T, which is going to be time, and T on like let's say 40% of that. So generally duty cycle you set it like 30% or 40%, and based on that you can calculate your on time minimum. Okay. Good. So this is how it was. Now DC minimum, DC maximum is fine. Coming back to the input voltage range. Okay, so input voltage range, if you want, you can calculate. Otherwise it's very simple, like for 5 volt input or 5 volt output, you have to keep minimum like 5.5 volt input or 6 volt input that we saw in the typical application diagram, typical characteristics was there. So generally it is not used like this. Always in industrial applications you will be having, let's say, 10 volt or 12 volt minimum for the input to get a voltage output of 5 volt. Okay, good. Let's get into the next one, which is uh, not this. Let's make it a little faster. Inductor selection. So inductor selection is very important. So the value of inductor L can be written like this: 3 multiplied by V output plus Vd divided by W. Okay, FSW, like switching frequency. So let us say we want to have 3 multiplied by V output is, let's say, 5 volt is there, right, plus 0.7 divided by SW is, let's say, 400 kilohertz. Okay, then what will be the value of this particular inductor? So it can be very easily shown that you can see 5 tiya 15, then 17.21 divided by 400, so it is going to be 4 चौका 16, 4 4 चौका 16, right, 400 around we'll see. Okay, and this is going to be 4 into 10 to the power minus 5, so that is 40 microhenry or something like that it will come, or 47 microhenry that it will come. So basically this is how you have to calculate, like this will be around 47 microhenry. So directly you calculated your inductor value based on this particular formula and switching frequency, right? So as I told you, as my switching frequency increases, like switching frequency operation, if you want to set it to higher frequency, then my inductor will be lower. Understood? Like my inductor will be lower when my SW frequency goes higher. Understood? And even for higher voltage output, the inductor value will be higher. So inductor will be higher for V output higher. Okay. Some of the vendors that is given already for the inductor selection, you can select it from Coilcraft or Sumada or Toco, even TDK is there. Okay, then Würth Electronics, Coiltronics and Murata. So I generally prefer, go ahead with Coilcraft or Würth Electronics, or like Murata. So they are more than enough. Even Sumada is good, right? Good. Now input capacitor we have already seen, like generally you can go ahead with X7R capacitor always for your design, because this is good. But for higher values of, like a voltage rating, let's say 47 microfarad, and we need 25 volt rating or 35 volt rating, you don't get X7R, so generally you go ahead with X5R, but not less than X5R. So X5R or X7R is always better, but X5R you go ahead with trade off for higher values of capacitor. Okay, generally you can go ahead with electrolytic capacitor as well. So electrolytic capacitor, in addition to that, you have to put like a ESR, low ESR values of 0.1 microfarad capacitor of ceramic capacitors. Okay, but make sure the electrolytic capacitor that you are using has low ESR value. Okay, that is equivalent series resistance should be low. Coming back to output capacitor, so output capacitor is generally calculated. If you want to calculate what is the output capacitor required, then you can go ahead with using this formula. So as you can see, as my output voltage decreases, so my V out is lower, my C out requirement will be higher. Okay, so that is one thing. So let us say for 3.3 volt output, the capacitor requirement will be higher compared to 5 volt output, or even 12 volt output. Okay, so as output decreases, my C out requirement increases, as you can see here. Similar to that, if SW pin is actually increasing, like the switching off operation is decreasing, then C out will increase. Okay, similar to that, output capacitor also you can utilize either electrolytic capacitor or X5R or X7R capacitors for your output settings. So recommended ceramic capacitors, you can utilize AVX, Murata or Thiouden or Visa or TDK. Okay, even like Samsung is there. Generally I utilize Samsung electromechanics, and we have Würth Electronics also, but they have little bit lower product range, but these are good. Even Camet is there. Okay, Camet is, AVX is a part of now Yageo, so not a problem. Okay, Good. So other parameters are, we have to see in the data sheet is uh, see boost pin and BD pin consideration. So there is nothing much was there in boost pin and BD pin. You have to just make sure that one capacitor is actually added at the boost pin to SW pin and BD pin. Okay. Now get into the application information. Okay. So what is application? If your V output is more than 2.2 volt, right? V output is, let us say, 3.3 volt or 5 volt or 7 volt or let's say 12 volt, then your BD pin must be connected to your V out, right? Your BD pin must be connected to your V out pin. Okay. Similar to that, if it is lower than 2.2 volt, like V output requirement is just, let's say, 1.2 volt or 1.8 volt, then VD pin can be connected to your input voltage. Okay. Rest others are same as we have already seen. Now coming back to enable pin. So enable pin, you have to understand, like enable pin can be directly connected to the input for very simple design. Okay. And if you want to have a voltage under voltage lockout design or something like that, then you can use a resistor divider at the input. So what will happen in the resistor divider? I'll tell you like this. So this will be my input pin, this will be my V input, and this will be ground. So my R3 and R4, let us say this, okay, this one. So this can be designed figure 6, right? So let's say figure 6 is here. So R3 and R4 can be designed like this to have a under voltage lockout. Okay. So what is the input voltage that you want, that you can put it, let's say I want it to be switched on at 5 volt. Okay. So in that case you have to design your resistors accordingly. Okay. So this is kind of threshold voltage that you want it. So what happens, why do we go ahead with this under voltage lockout? I'll tell you. Let us say your input voltage is 12 volt. Okay. So you do not want the system or do not want the IC to give you V output unless my input is, let's say, 10 volt. Okay. So what you can do is V input lower, you can set it to 10 volt. So for that, 10 is equal to, let us say, R3 you are going to set let's say 100 kilo ohm. Then R4 can be calculated using this formula. Okay. So R4 can be calculated using this formula. So it is very easy now. Understood? So what will happen? This will be 10 R4 is equal to 100k plus R4. My R4 will be 100k divided by 9. Understood? So this is how you will be getting around close to 9.9. How much it is? Yeah, 9.1 kilo ohm, right? So R3 and R4 has been designed. Okay. You can keep it little bit higher values, let's say 200 kilo ohm or 330 kilo ohm or something like that, to get little bit lower current into the enable pin. But I'll suggest my is connect the enable pin directly to input voltage. You don't have to worry about your under voltage lockout and all. Okay. So this was the enable pin to design under voltage lockout. Now if you have to have a sorted input protection or something like that, you can put additional diode at the input, and similar to that you can keep one diode at the output as well from the battery, so that it doesn't go in reverse direction. Okay. Have any questions regarding the sorted input from or prevents the sort or protection at the input or reverse or input, then you can always reach out to us for a detailed explanation about this kind of designs. Okay. But it is very simple. What is a very simple design is, put one diode at the input, make sure the current rating of this particular diode as well as the reverse standoff voltage, like voltage rating, is according to the input voltage, right? So let us say if you have a 12 volt application, use a diode of minimum 40 volt ratings or 60 volt rating. Okay. You can go ahead with a little higher voltage or rating also, let's say 100 volt, but don't go ahead with lesser than 40 volt rating. Okay. Let us say we require 30 volt operation, then definitely you have to go ahead with 100 volt or 200 volt diode. Okay. That's the understanding. Okay. PCB layout guidelines they have given you. So a good PCB layout guidelines, as you can see, like this is the IC that is there, DFN package. Okay, similar to that MSOP package also will be having same. And we have inductor connected to the this is my SW pin, so connected here, and this is my Vout. Okay, and this is how, if you want, you can go very deeply into this particular understanding. So this is my ground plane that is there. Below the IC also we have ground, and this is the ground all over, like a plane that is connected. Okay, so this is my input pin connected with one capacitor. You can have a series of capacitor like this only. Okay, similar to that we have output pin, so connected to the capacitor is here, so we can have several more capacitors that you want. Okay, this one we have power good output pin is here, so like that. So okay, you have a good understanding now. Now what we'll do is, we'll just see some of the applications that is there. But since like we have spent quite a lot of time in explaining this particular data sheet, so we'll continue this particular session in our next session for typical application explanations. So we'll explain each and every applications one by one, like how they have designed this particular values of inductors or resistors to set the output voltage, or what is the input capacitor, what is the output capacitors, so that you can have a very good understanding about how to design a particular circuit of typical application of 3.3 volt and some other voltage ratings as well. Thank you so much.